All right, the next video for Unit 3 is going to be on the theorems. So the first theorem we're going to look at is the intermediate value theorem. And there's a definition there you can read through, but I would rather use an analogy. So imagine that you are, well, some of you drive, some of you are passengers. So you're either driving or you're a passenger. And you're on a long road trip, okay? So when you look out the window, you see mile marker 63. And then you go back to your phone or whatever, or you're watching a movie if you're a passenger, and then you see mile marker 67. So basically the intermediate value theorem states that, well, what happened between 63 and 67? Well, to get from 63 to 67, you had to pass mile marker 64, 65, and 66. So even though you didn't see them, you know that when you saw mile marker 67 that you had to have passed those, all right? Because to get from 63 to 67, you have to pass 64, 65, 66, okay? So you don't know exactly when you passed them, you don't really care, but you know that they exist, all right? And that's all the intermediate value theorem is that it's an existence theorem. So if f is continuous and that continuity for you was the road, like you're driving on this road, assuming that there's no obstructions, but for us to use the intermediate value theorem, the road has to have no obstructions on a closed interval. So we knew we went from 63 to 67. That's our closed interval, such that the outputs aren't the same, which, like, that's saying we went from mile markers. Actually, no, we'll talk about that in a second. So we'll leave that part alone for a second. And k is any number between f of a and f of b, then there is at least one number c such that f of c equals k. So it's a bunch of numbers, of course, but it's just saying if we think that this is a and this is b, we have a point here and a point here, and it's a continuous function, okay? We are just going to say that there is at least one number in between here, c, such that we'll have an output here. And that output will be between f of a and f of b. Okay, so there's a couple ways that you're going to be seeing this. This is something also that you will not be assessed on. It is a calculus topic. So you will see it on your ICAs and your homework, but you will not see it on the quiz or the test, okay? So how can we apply this to a function? So given the function f of x, can IVT be applied to f of x on the closed interval from 0 to 1? Well, a condition for IVT is that it has to be continuous and on a closed interval. So f of x is a polynomial, which means it is polynomial, which means it is continuous. Okay, so yes, the intermediate value theorem, or IVT, can be applied because f of x is continuous. Now, if we wanted to go further, we could say f of x is continuous on that interval. So that means you can have a function that has a discontinuity, but as long as it's not in the interval that we are applying IVT, you can still apply the intermediate value theorem of that on that function on that interval. So part B, is there a 0 on the interval from 0 to 1? Well, let's think about it. If I want to find a 0, we'll call it C, and it's within the interval from A to B. Let's say that we start down here. We'll call this f of a. It's the output for A. And then up here we have the output for, whoops, that should just be a tick, the output for f of b. So this function is continuous, and at some point it passes through the x-axis, which would be our 0. In order for that to happen, f of a would have to be a negative output, and then f of b would have to be a positive output, or vice versa. If the function was decreasing, the roles would be switched. So whenever we're finding a 0, you test the endpoints. And see, do their output values change? So we'll do f of 0 is equal to 0 cubed plus 3 times 0 minus 2. So we get -2. Oh, cool. We'll call that -2 then. And then we'll plug in f of 1. So we'll get 1 cubed plus 3 times 1 minus 2. And we end up with +2. Cool. We'll call that +2. So again, think of the mile marker. We went from 63 to 67. We may not know exactly when we passed the other mile markers, but we know that we did because we know they're in between 63 and 67. Same thing, if we go from -2 to +2 and we travel along this continuous function, at some point there's a 0 in there. There's a solution. I don't know when it occurs, but I don't care. It's just an existence theorem. Like we could find it if we wanted to, but that's not what it's asking, okay? This is just asking, does that point exist? And the answer is yes. There is a 0 on the interval 0 to 1 according to IVT. So again, you will not be assessed on this in this class, but you will see it next year in calculus if you plan on taking calculus. So if you were in class for this lesson, projectile was throwing markers across the room, maybe a couple pins as well, not in the direction of any of the students, just across the board, just so that we can get a feel or try to remember what does projectile motion look like. So I threw a marker in the air, and then like thinking about wind resistance and gravity and all that, it will create a parabolic path. So a projectile following a parabolic path has an altitude of 100 feet at time t equals 0. Let's draw this so we fit their interval. Let's call this t is 4. We'll call this 100. And an altitude of 550 feet at 7. Go here, and it's parabolic. Cool. Explain why the projectile will have a height of 350 feet on the interval from 4 to 7. So this is why I go back to the mile marker analogy every single time. Like, we know that this is 100. We know that this is 550. At some point, that projectile will pass through an altitude of 350 feet, all right? I don't care when it happens. Like, it's not asking me at what time. And again, we could figure that out if we wanted to. But at some point within this interval, it does pass an altitude of 350 feet. And I should have mentioned this before, but it's projectile, therefore it is continuous. So projectile paths are continuous. Because it's a quadratic, it's a polynomial. Okay, so there's two things that we need to talk about with this. The first one, we know that yes, it will pass through 350. So it will have a height of 350 feet on the interval 4 to 7. Because the path is continuous and 350 feet is between 100 feet and 550 feet. So in my explanation, I'm referring to the horizontal pathway, stating that it's continuous. And then I'm also referring to the altitude, about how 350 is in between 550 and 100. So again, it's just an existence theorem. It's just showing that something is existing within this continuous pathway. All right, so the next theorem is going to be the remainder theorem. The remainder theorem, it states that if a polynomial f of x is divided by x minus c, then the remainder is c. So this is just stating that whatever the factor is, if we plug that into the function, we will get the remainder, which is the same as the output, okay? So this says find the remainder when f of x is divided by x plus 3. So with this remainder theorem, we're able to find what the remainder is without actually going through synthetic division, okay? So we want to use the 0 of x plus 3. Because if you notice up here, it's minus, so that means you use the opposite, okay? So the opposite is x equals negative 3, or the negation. So that means we'll plug in negative 3 into the function. So f of negative 3 is equal to, I plugged it into the calculator, I got 23. So if we were to synthetically divide x cubed plus 7x squared plus 3x minus 4 by x plus 3, we would have a remainder of 23, which is going to be the same as the output at x equals negative 3. Okay, so your remainder is your output, which makes sense because when you synthetically divide by a factor with a remainder of 0, that means it's crossing the x-axis, okay? So this plays directly into the factor theorem, okay? So the factor theorem is saying let f of x be a polynomial, then that means x minus c is a factor of f of x if and only if the c is a 0 of f of x. So that means we are doing the same thing we did for the remainder theorem, but now if your remainder is 0, that means that is a factor of the polynomial, okay? So because 23 does not equal 0, this means that the factor x plus 3 is not a factor of f of x. Okay. So now let's look at the remainder theorem and factor theorem, they kind of work together, okay? So let's look at A. So we have f of x and it's asking, is x plus 1 a factor? Okay, well, I'm going to use the remainder theorem. So when I use the remainder theorem, I can determine if it's a factor. I don't need to actually use synthetic division. So the solution for this factor is negative 1. So I'm going to plug in negative 1. So we have negative 1 cubed plus 2 times negative 1 squared minus 3 times negative 1 minus 4. We end up with, I believe, 0. Okay, so our output is 0, which means that is also our remainder. All right, because it's 0, therefore, x plus 1 is a factor of f of x. Cool. All right, so we found a factor for this. Now it's asking, is x minus 2 a factor? Okay, well, the solution for this one is x equals 2. So we'll do f of 2. When I plug in 2, I'm going to end up with 6. So because I have a remainder of 6, that means the output is 6. So at 2, the output is 6. That means we're not crossing the x-axis there. Now for the first one, at negative 1, whoops, let me fix this. At negative 1, our output was 0, therefore it was crossing the x-axis, okay? So that means it is a factor, it is a solution, but negative 2 is not. So therefore, x minus 2 is not a factor. All right, so write f of x in its factored form. Okay, So, side note, we know one of the factors by using the remainder theorem in part A. We know that x plus 1 is a factor. So because I know x plus 1 is a factor, this means I know that it has no remainder if I were to divide it, okay? So that means we can use synthetic division in order to factor it a little bit further. So we'll use -1, and then we'll have 1, 2, -3, -4. So again, I know that x plus 1 is a factor, which means it has a remainder of 0, which means I can do synthetic division, and I should end up with a remainder of 0. Not should, I will, because we use the remainder theorem to confirm that. So we know that x plus 1 is a factor, so we need to find the other factor. So we use synthetic division. So 1 multiply, we get -1, +1, -1, -4, +4, and here. Okay, so that means we have f of x. We already know x plus 1 is a factor. And then with synthetic division, the original function was x cubed. So this one will be x squared down here. So we have x squared plus x minus 4. And this is not factorable. These solutions are, I can't remember. They are either irrational or complex. But if we were to graph it, we could find it. But you would have to use something to find those. All right, the last theorem is going to be the rational root theorem. So up here, we were basically playing guess and check. Is x plus 1 a factor? Sure, let's try it. Okay, cool. Is x minus 2 a factor? Okay, cool, let's try it. We're just kind of guessing from a realm of infinite numbers. But there is a way to limit what your choices are, okay? So the rational root theorem states that if we take the constant, which is 4, and we take those factors, so I'm going to make a set, so I'm using the curly brackets. The factors of 4 are 1, 2, and 4, and the factors can be positive or negative. And we take the factors of the leading coefficient, which in this case is +6. So the factors for that are 1, 2, 3, and 6. Those can also be positive or negative. If we take the ratio of these two, we will find a list of possible rational roots for the polynomial, okay? So you're not just guessing random numbers. You actually have a set that you can choose from to use the remainder theorem and test if they get a remainder of 0, aka an output of 0. So when we do P divided by Q, how I structure it is I do 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 6. You want all of the possible ratios, okay? So we'll have 1 divided by 1, 1 over 2, 1 over 3, 1 over 6. And then we will repeat that, 2 over 1, 2 over 2, 2 over 3, 2 over 6. So we'll have 2 over 1, 2 over 2, 2 over 3, 2 over 6. And then next, we'll have 4 over 1, 4 over 2, 4 over 3, 4 over 6. So 4 over 1, 4 over 2, 4 over 3, 4 over 6. Okay, and then we can't forget the plus or minus. We chose some popular numbers here. All right, so now we want to kind of trim some of this. All right, we have some repeating values. Having repeating values in a set is okay, but you want to try and limit it to where you're not repeating, because think about it, you don't want to have all of these values and then accidentally test the same value twice in the remainder theorem. You're just wasting time at that point, okay? So 1 divided by 1 is 1, and then we have our 1/2, and then 1/3, and 1/6. So none of those are repeating. And then we have 2. We don't have 2 yet. 2 over 2 is the same as 1, so we're not going to rewrite that. 2/3 is new. And then 2 over 6 is the same as 1/3, so we won't write that. We have 4. 4 over 2 is just 2. And then we have 4/3. And then 4 over 6 is just 2/3. Okay, so these would be our possible rational roots for f of x. Luckily, we're going to change functions because that's too many possibilities. And we're not going to make you test that many either. Okay, usually we'll give you roots and then you'll have to go from there. So let's try this one. It says factor f of x. Okay, so I don't know, where do I start? Let's try our p's and q's. So I'm going to make a list for my p's, make a list for my q's. So the p is going to be the factor of the constant. So we'll have plus or minus. Yay, it's prime, so I only have two numbers in my set. And then the q is going to be 3, and again, prime. So we have 1 and 3. And we're going to take the ratio. All right, so p divided by q. We'll have plus or minus. So in our set, we'll have 1 over 1, 1 over 3, 7 over 1, and 7 over 3. And this will reduce to, we have plus or minus. We'll have 1, 1/3, 7, 7/3. Okay, so we use the rational root theorem for this. Rational root theorem. Now I want to use the remainder theorem to try and test which one of these will be a solution. Let's try 1. So if I type in f of 1, we get 3 plus 5. Oh, minus 31. That was a bad choice. All right, so that's definitely not going to be 0. All right, I don't know why I chose that. All right, but it's not going to be 0. All right, let's try 7/3. So f of 7/3. So f of 7/3, you have a graphing utility, and if you store this in y1 or you trace it or I plug it in, I get 0. Okay, so that's all I need. All right, I finally found a solution for this, and it's going to be when x is equal to 7/3. So as a factor, that is going to be x minus 7/3, which is going to be, we can rewrite this so that the 3 is with the x. If this, so let me show this with the algebraic steps. So we have x equals 7/3, all right? In order to write the factor, you want to have everything on the same side equal to 0. So I'm going to multiply both sides by 3, and then I'm going to subtract by 7. So that will be, this is my factor, 3x minus 7, okay? So it's asking us to factor, so that's what I want to use. But I only have one factor. So now I know that based off the remainder theorem and the factor theorem, okay? So this is also the factor theorem. Well, remainder theorem's up here, factor theorem's down here. Based off the factor theorem, my output / remainder will be 0. So to find the other factor, we will use synthetic division. So the coefficients for the original function are 3, 5, -31, and 7. Bring down the 3. 3 times 7/3, we get 7. 5 plus 7, we get 12. 12 times 7/3, we can reduce that to 4, reduce this to 1, so we get 28. -31 plus 28, we're going to get -3. -7 over 3 times -3, we get -7 with a remainder of 0. So our factored function is, we have our 3x minus 7 times 3x squared plus 12x minus 3. And I knew it was squared because the original degree is 3. So we'll go down by 1. And we can actually factor this a little bit further. We can factor out a 3 from that trinomial there. So I'm going to make this a little bit smaller so you guys can see. It's really small. Oops, where'd it go? There we go. All right, so this will be equal to 3x minus 7. Let's put the 3 out front. And then we're just left with x squared. 12 divided by 3 is 4. And then 3 divided by 3 is 1. Or negative 3 divided by positive 3 is 1. So that is our factored form. All right, so now at the bottom, it says find all of the zeros for the same function. First, find one of the rational zeros of using a calculator, by using a calculator. We already did find it. It's x equals 7 over 3. If you plug it in the calculator, you'll see it cross the x-axis there, and you can find that, okay? So x equals 7/3 is a solution but actually let me rephrase that because we want to use the factors. So we'll say that 3x minus 7 is a factor, but x squared plus 4x minus 1 is a factor, but it's not factorable. Which means we don't have a rational number that we can use to create two factors for this quadratic, okay? So that means we need to use the quadratic formula. And you do not get a formula sheet for this class, so you do need to remember your quadratic formula. It'll be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And again, we use the quadratic formula to solve for irrational solutions and complex solutions. So based on what happens under the square root, that's what's going to tell us. And then again, this is why complex numbers have conjugates, is because of the quadratic formula, because of that plus or minus. Okay, so using this, our non-factorable trinomial, our a is equal to 1, b is equal to 4, c is equal to negative 1. So now we'll plug those into the quadratic formula. So we'll have 4 squared minus 4 times 1 times negative 1 all over 2 times 1. All right, negative 4 plus or minus. We have 16. Looks like this will be plus 4. So this right here shows me that we will not have complex solutions. It's just irrational. So that means when you graph it in the calculator, you'll see 3 x-intercepts, but 2 of them you will not be able to turn into a fraction because it's not a ratio of 2 integers. So we'll have negative 4 plus or minus the square root of 20 over 2. And if we look at this, we can do the square root of 4 times the square root of 5, because that's the square root of 20. And then the square root of 4 will be 2. And we can see that, I'm going to go ahead and split these up. Negative 4 over 2 plus or minus 2 root 5 over 2. Sometimes a lot of people will try to reduce all of these, or not reduce all of them. They will only reduce 2. Like this could be a 3 and then they ignore that. You can't do that. Okay, if you're trying to reduce, every term needs to be able to be reduced by that same factor. So splitting it up, you're able to kind of keep yourself in check. So we have negative 2 plus or minus root 5. So all the zeros, so the solutions for f of x are x equals 7/3 and -2 plus or minus root 5. So there's our two irrational solutions. All right, those are the theorems. Again, you will not be assessed on the intermediate value theorem, but you can expect the remainder theorem, factor theorem, and rational root theorem on the assessments.